Alrighty, so I guess we're missing Kaylee today. Looks like it. So what is today? 9/22. I think I left my pen at the wellness, my other pen at the wellness. I'm very sad. Okie dokie. So opened up Module 4, which is Chapter 3, and I need to add, at least I feel I need to add some instructional content videos yet to make up for what we don't have time for in here. And so I'll try to get to those. I do have some things up that are hopefully helpful, and we'll look at a little bit at those today. Questions on anything right now? Nope. Not very inquisitive today, I guess. So, alrighty then. Well, Chapter 3, we actually get into how most people, if they're analyzing data and running hypothesis tests to help them come to conclusions about the data and the processes from which the data came and all that. Chapter 3 finally gets into that. And what we're looking at in Chapter 3 are categorical data. And so the way this tends to be summarized is as counts. Okay, we tend to count, how many of each category, and so we tend to summarize as counts. They really, we do two things, really, as far as the hypothesis testing, and we do have a little bit of the confidence interval things. The confidence intervals are nice in that I think for a single proportion they make a lot of sense. For the difference of two proportions, I guess it comes up quite a bit, but at the same time it's to me limited. So we do have confidence intervals. Intervals for estimating proportions. Okay, so if you're just out there, you just want to estimate a proportion, you're taking data and you kind of like, oh, well, what percentage of people stop at stop signs? It's probably like 0. But what percentage of people stop at stop signs? You don't know what that, maybe you have no idea what that number is. And so you go take some data, you get a proportion, and then you say, well, that's probably not truly the proportion. Can I put some confidence bounds on that? And so we'll look at calculating that. We'll do it we have it, I guess, for both a single proportion and the difference of two proportions. But again, I'm probably myself more just interested in the single proportion for something like that. And then we have our hypothesis testing. Okay, and then again, that we'll look at a couple different cases. We'll look at proportions. Well, how about data, proportion data against a known value. Now, known, and I could put that in quotations or something like that, but you know, because, well, how is it known? You know, I mean, is it just what you are calling known? You know, it's our null hypothesis is what it is, and sometimes we really do know that number, and other times, well, in a way, it's sort of a hypothesis itself. But so we'll look at proportion data against a known value or values, and then proportion data for two variables. Okay, so we'll look at that and in our hypothesis testing. Okay, so kind of following the text a bit, I'd like to pull this up. Where are we? Whoops, I don't know what I just did, but hey, this will take care of it. Okay. Oh, wrong thing. Silly me. All right. Now there's a sort of a weird thing in your textbook. So this is right at the beginning of chapter 3, and it's talking about when we can use the normal distribution to help us with proportion data. And what's weird about the textbook is they give us different answers in different places. And so I just want to point this out and kind of show you what I started with last module was, you know, if n times p, your number of samples or your number of trials with your proportion of success, if n times p is greater than or equal to 5 and n is at least 20, you do pretty well. Here, in this one, they don't mention really n by itself at all, but they give a much higher number for n times p. They say 10, so twice as big. And of course, generally speaking, whenever you're using the normal distribution on things, you are assuming that your observations are independent of each other. So 10 versus 5, and where does n come in? Well, so I thought I'd just go to Desmos here and just kind of show you. I did this quick thing with a normal and a binomial distribution because the binomial distribution is actually what the proportions are behaving like if they follow their rules, being independent trials and all that. So those blue or purple or whatever they look like dots are the values of the binomial distribution, and they should only be at particular values of n. Well, sorry, of x really, because n is capped at 20. And they should, you know, if I'm going to use the normal approximation for it, they should fall pretty close to that normal curve that we have there. And so I have n equals 20 up there, and n times p is 5, and n times 1 minus p is 15. So they're both bigger than 5. Now the reason you need to check both is because it's symmetric. A failure is in name only, or a success is in name only. And so what you're actually asking is the expected number of successes at least 5, and is the expected number of failures at least 5. Okay, and if so, then actually this tends to do pretty well. You know, you can see the dots there. Now, what's interesting is I haven't really looked at it that closely in a while, but because of how the approximation works, you don't necessarily actually want those dots right on the curve. You might want them a little ahead of it or a little behind it, depending on where you are. And so, you know, as you look at that, it does pretty well. The very middle at 5 right there, actually that dot is a little bit below the top of the curve, and that's sort of bad, but it's not off by that much. Okay, so you know, what you can see there is that the data do follow the normal curve, or well, the binomial distribution follows the normal distribution pretty darn well. And that's for n times p at least 5, n times 1 minus p at least 5, and n at least 20. Now, if I take p down quite a bit, then you can see where the problem starts and where we can have some issues is, for one, a whole lot of the normal distribution is in the negative area there. I mean, stuff that's tall so you can see it. This stuff in here, it's in the negative values of x. Well, I can't have a negative number of successes. I can have 0, but I can't have a negative number. And so you see things can start falling apart. And so it doesn't work so well. So that's why we would like to have values, you know, of n times p or n times 1 minus p. You know, the expected number of successes to be usually at least 5, expected number of failures to usually be at least 5, and n being at least 20. And again, the textbook, in this particular spot, it says we want 10. In another spot, it uses 5 and says n equal 30. And then in yet another spot, I think it just says the n times p being at least 5, but doesn't really talk about n. It's the number overall. And so I'm not sure why. Because I really like the authors. I think they're pretty good, but they're kind of all over the place for that, and yet they're all the same idea. So I'm not sure what's going on there. But okay, so I just wanted to point that out because it is in the text that way, but we relax it a little bit. We don't say it has to be that high. I'm thinking we might want to. Do we want to close that door? Is that kind of disturbing having that come in? I don't listen to myself, so I can't tell. But okay. All right. So let's get into the confidence interval stuff and all that. So again, the idea is that what we're really working with are those dots. Okay, that's truly what we're working with, kind of a bar graph if I put lines underneath those. But we're using the normal distribution as an approximation. Nowadays with technology, I don't think that's quite so necessary. However, it's kind of the way everything's set up now. You know, that's because of the history of it, that's just kind of how everybody does stuff, so that's the vocabulary, and I think it makes sense to kind of go with that same flow. So, okay. Oh, I need to switch, don't I, here? Okay, switch back to here. All right. So for a single proportion, you know, so you may take some data, and you may get S equal the number of successes. And again, a success and a failure, those are technical terms that have nothing to do with morality or luck or anything like that. You know, so a success in the sense of human behaviors and so forth, a success could be something we don't want. Okay, so like if you're in the judicial system, looking at that, recidivism, you know, people going back into the system after they get out, that's a bad thing. Nobody wants that. Yet, if that's what we are counting, it would be called a success. Okay? So success does not mean a happy thing necessarily. It is just whatever we're counting. So S is the number of successes. N is the number of trials. Okay, or observations. Let me go with observations. And so then what we call P hat is just that proportion of successes out of the number of observations. So P hat's just S over N. Okay, and then what we'd like to do is be able to create this confidence interval. Typically for us it's a 95% confidence interval, because that's the alpha equal 0.05. And so we're just trying to get some bounds on where we think the real value might be given these data. And so to do that, our confidence interval okay, and for a mean is really always the same idea. And notice this is the number of successes divided by the total number of observations. This is a mean or an average. You know, the average number of successes is going to be a proportion in this sense. So so that is an average, and so when we produce that, we take the data average that we, you know, our sample average, in this case that's P hat, and then plus or minus, so we just move from right or left in each direction, and we go Z, and the notation is Z alpha over 2, that's all one symbol. And then times the standard error. And so Z alpha over 2, again, is just our number of standard deviations. Okay, how confident do we want to be? How much of the population do we want to put in there, right? So again, you know, you have this normal distribution, and when you do this Z alpha over 2 thing, what you're doing is you're saying, I want to include this much of the population. whatever that is. And if this much is a total of 1 minus alpha, out here we have alpha over 2, and there we have alpha over 2, and that's where they get this thing of calling it z alpha over 2. So generally speaking, okay, generally we have alpha equal 0.05. Almost all the time. Okay, this actually, this particular project, you will change that for a couple things. Okay, and I'll have videos on that and so forth, but that can, as we look at some particular cases, we can change that. But generally, it's alpha equal 0.05. We're doing that for everything. And so, 1 minus alpha is 1 minus 0.05, or 0.95. 95% confidence interval. And in that case, z 0.05 over 2, so again, that's just all a symbol, and typically you don't write it as 0.025, right? You could do that division, but typically you just don't. Okay, because it's part of the notation is pointing out that we are doing this symmetric interval of the normal distribution. And that is 1.96, or about 2, right? A rule of thumb says, yeah, you know, it's about 2 standard deviations. Okay, but that's all it's really saying is how many standard deviations do you want to include in order to get that particular alpha or 1 minus alpha, whichever way you talk about it. So with confidence intervals, we tend to talk about the 1 minus alpha, the 95% confidence interval, or the 90% confidence interval, or something like that. But, and I don't know why. And it's just the way, I guess because it sounds good, you know, maybe historically, again, that sounded right. But so, almost all the time, we would use 1.96. So then we know how to calculate p hat. We can look up z alpha over 2, and then we just need our standard error. And so our standard error in this case is our p hat, well, the square root. Square root of p hat times 1 minus p hat over n, and that's all underneath the square root. And so, you know, that's how we calculate it. Now, where does that come from? It actually comes from the binomial distribution. So, if you study probability and statistics and you learn about the binomial distribution and you learn about its standard error, that is exactly how you calculate it if you know n and you know the probability of success. You can show that the definition of its standard error is that. Okay, it turns out to be that. And so that's where it comes from. In a lot of ways, we don't really care. You know, if you have to learn much more about probability and statistics, then you'll care. But for a lot of what you do, you know, or might do, you probably don't really care. You just, what you want to focus on is it's a standard error, and what the heck is a standard error? You know, so, you know, those are the things you should think about. You know, if we mention various things like standard errors, and you're kind of going, what the heck what is that really? That's what you need to look at. As far as calculating it, for the most part, we've got technology to do that for us. We don't have to actually remember how to calculate any specific standard error. We just need to know what it means. You know, what the heck is a standard error, right? And that was a standard deviation of a sampling distribution. Oh, okay, what's the standard deviation? What's the sampling distribution? Sort of never stops, right? You know, a lot of vocabulary. But those are the things you want to make sure you know. Don't get hung up on calculations like this, because again, technology will pretty much do it for us. Okay, now, so once we calculate those, we've got our confidence interval. You know, so if we have something like you know, our data, maybe we had, let's see, we had, let's go with, how many are in here? 10? 9. So we had, last, you know, when we were talking about the simulation, you know, we said, well, what if you have 6 females out of 9, and they were in this class, and we were asking about the proportion of males and females, if it was 50-50 and all that. So here, you know, okay, we could just look at this class on any given day, and today we're actually missing one person, and so we have 5 female, 3 male. And so and before we were, I think we decided success was a female. We counted the females, and so our data had, in this case, we'll say 5 successes. Okay, for 5 females in class. So this was S. Sorry, left off the S. N equals a total of 8 in class. Okay, so we have that. And so that means our P hat is 5/8. And what is that as a decimal? Like 0.625 or something like that? Yeah, I think 0.625. Maybe it's 6215? We'll get to it in a minute. We'll look at it. So there's our P hat. Well, we better get to it right now, because then I need it for the standard error. Right? So I've got a spreadsheet up. I have decimals up as well. So I'm just going to go to this decimals and click in here. And what do we have? 5/8. 5 divided by 8, 0.625. I should have gone with my gut feeling. All right, so 0.625. And so now our standard error, square root of 0.625 times 1 minus 0.625, all divided by 8. Underneath that square root. So I can do the same sort of thing here. Now I'm going to oh, I better not, because I've already got P defined somewhere else. So so here's my square root, and I have my point .625 times, times 1 minus .625, and that's .375, so .375, and then divided by 8, and that is .1711. 0.171, it was, no, 12, I guess. There's 6. And so we've got our standard error. And so now I can compute my confidence interval for that proportion of females, and I think we were counting biology, nursing, and psychophysiology, and business, or accounting, or something like that. And so our confidence interval is our 0.625 plus or minus 1.96, that's a 6, times whatever I said, 0.1712. And so I can multiply that out. I can actually do those addition and subtraction.
Would you not divide both numbers by 8?
Well, it is dividing the product by 8.
Because when I multiply those numbers together and divide by 8, I get a different number. I think.
Did you take the square root?
Oh, no, I didn't do square.
Ah,
Okay.
yeah.
Thank you.
Yep. So, so here I'm going to call this S equals, so I can use it down here. And so if I take my 1.96, I guess, 1.96 times S, and actually I'm going to call that M. I'd like to call it ME, but I don't want to, because that, didn't I define S? M equals 1.6 times, how come it didn't like that? Did I use S somewhere else up here? Ah, yeah. Okay. We'll just call it V. And V. I could get rid of all that stuff up there, I guess. But I call it M because this quantity right here is called the margin of error. A lot of polls being done these days, right? Election coming up, everybody's, is it Trump, Biden? Is it in Kentucky? Is it McConnell, McGrath? Right? And so they go take a poll and they get a proportion, and then they say the poll's margin of error. Yeah, that's all they're talking about. Confidence interval. That's it. Nothing more than that. And so our margin of error is 0.3355. So this is 0.625 plus or minus, and actually I guess I'll just go with 0.335. Same number of decimal places. And so there's our confidence interval. And if I do that addition and subtraction, then what I'm guessing is that we're going to say, oh, we've got a 95% chance that the right answer is inside this interval somewhere. And so subtracting that, I get 0.29. And adding it, I get 0.96. Now, so because we had such a small number, right, our confidence interval is almost as big as it could be. Right? It's almost to 1, and that's as big as the proportion could be. And, it's down here at 0.3. I guess, it's got a ways to get down to 0. But it's we're saying, well, the right answer is somewhere between about 0.3 and 1. That's the problem with small data sets, right? There is a lot of variability. We aren't sure. But that's all we're doing with confidence intervals. Any questions about that? So for the hypothesis test, we got a couple different things going. So in 3.1, our hypothesis test is, and actually the confidence interval came from 3.1 as well, it's just a single proportion against a known value. Okay, so we're just asking, is the proportion for whatever we're studying, our hypothesis is that it's some p0, some known amount. And then what we're going to do, we're going to stick to two-sided alternatives. And so our alternative is it's not. And in this case, we assume we're going to, as long as the numbers are big enough. Now, for our little situation here, they aren't big enough. We don't have 20. So I wouldn't feel comfortable using a normal distribution for what we just did here with that confidence interval and so forth. I'm not even sure I feel that comfortable with it here, but actually with confidence intervals, it's done this way all the time. So we'll go with it. So our null hypothesis is, that this is something known. How is it known? Well, again, in our previous module, right, what we decided was known was the rate at which the general population of physicians reported bias. And that was like 59%. Okay, so we would just say, well, okay, so the null hypothesis is that our proportion of our data that we pulled from our sample is that 59%. And then the alternative is, no, it's not. And in this case, to do a normal approximation, you turn everything into a z-value. Okay, and z this is a standard normal. Now, again, with technology, you don't have to get too worried about this. Okay, but all we're doing is we're taking our data and looking at it in terms of numbers of standard deviations. Okay? And so to get that normal number to be able to look it up in a standard table, we take our data, so p hat, that's our average that we sampled, that we got, minus our null hypothesis average. Now again, these are proportions, but proportions are averages. So we're just taking our data minus the hypothesized proportion, because that's the mean of our null hypothesis. That's what we're assuming is happening. Our assumption is when we sampled these data to get this p hat, we were sampling from a population just like this one. Every time, whatever the null hypothesis is, that's what we're assuming we're sampling from. Now, may be wrong. It may be that we'll get such a small p-value that we won't believe this. But for now, to calculate our p-value, we base it on assuming that our population is built like this one with this proportion. And then, so we're finding how far are we from our hypothesized average or proportion. So that's the total distance. But now you have to normalize it by number of standard errors. So you divide by the standard error. And so in this case, when you divide by that standard error looks like P0 times 1 minus P0 over n. Now this is one distinction I think is reasonably important to kind of get the idea of. Is notice these formulas look the same, except for one little thing, is that here I use P0, there I use P hat. Okay, well, if I'm doing a confidence interval, that's all I know. I don't know anything else. I don't know the hypothesized distribution. Right? So the best I can do is P hat. But here in a hypothesis test, I'm telling you, we are assuming and basing our calculations on that population with that proportion of successes. And so we know it. Oh, well, so we use it to get our standard error. Okay, same idea, it's just here, that's our population we're assuming. Here, we don't have a population to assume, and so we do the best we can. Now, for something like this, so this calculates it, but in the instructional content, I put 4 templates and then also videos as to how I made them. And just in case, well, I think partly I made the videos at one point because I thought I might have you make the templates. I decided not to. Okay. But if you look at these templates, you can go there and use actual data in these. And this says this is a 2-sided hypothesis test for a single proportion. And the reason I made these in Desmos is I'd like you to use them to actually calculate problems like from the homework and so forth, because it gives a graphic of what's going on. And this one is definitely much better labeled and so forth than the other 3. But I also think this is really the important one. If you really get this, then the others aren't that big a deal. And so we've got a 2-sided hypothesis test, and it says H0 is that P equals P0, and the alternative I use 2, a less than and a greater than as a not equal. They don't have a not equal sign in there. And so P0, if I went ahead and used the example we just did in class and said, Again, we really shouldn't, but we've got data. And if we assume from last time that our P0 was 0.5, okay, so I can put in 0.5, and then number of successes is, what was it, 5. And number of failures, I could use a slider, but it's probably just quicker to type in the numbers. 8. Oh, wait, no, number of failures, sorry. Number of failures is 3, because n is 8. And at that point, we're done, and we can get a p-value down here. And the p-value is nearly 0.5. It's 0.479. And what you can see up there is actually the orange and the green, okay, these, and I don't remember which is which, you know, well, we had 5 out of 8. So the green, I guess, is our data. Okay, so our data came in here at 0.625. And so as far as our normal approximation to what's going on, our data took up this much of the population. Okay, so we can see it graphically, that it took up that much of the population. Now, it's a two-sided test, so we had to add in the area on the other side as well, because we could have been either above or below. And so the orange is doubling the area. And that's the total area, and that comes out to nearly 0.5. And then these dashed lines are showing us where alpha equal 0.05 would be. And if we have any area inside those lines, we will fail to reject, because we will be over the 0.05 threshold. And so, you know, it's a visual of what we're calculating of this normal distribution that we're assuming. Okay, so we're, by assuming, you know, here's the 0.5, it's right in the middle, right? So the normal distribution here has a mean of 0.5 and a standard error or standard deviation of whatever we had, 0.171. And so graphically, that's what our population looks like, how it's spread out. And then we can mark off where we get 5% outside and 95% inside. So that is, you know, those lines are at about 2 standard deviations, actually 1.96 standard deviations on either side. Okay, so they mark where our data need to be. And our data were way in there at 0.625. They needed to be way out past 0.8 somewhere. Right, so if, you know, the question is, well, you know, what if we had sort of 10 times as many data? What if we had 80? So what if we had 50 and 30? And so n would be 80. And notice what happens is all of a sudden we would reject the null hypothesis. Whoops, we're going wrong. What's going on? It sort of doesn't seem to matter which way I rolled the mouse. It zoomed out. That was kind of weird. But what you see now on this is our p-value is down to 0.025, and those areas are outside. So same proportion, 0.625 for our data, but we had a whole lot more data. Now, and again, these are in the instructional content. I embedded them in there. That could be a bad idea. I don't know. But I also have a link. So, you know, if you were to click that, it would go outside of Blackboard and open up Desmos and do it there. Okay, well, that was interesting. Oh, wait, no, it didn't. I was going to say, it kept the same picture. No, it didn't. So, okay, so that gets us started on all this. Like I say, I've got a lot of content videos to add, but we do have these templates, and I guess that'll do it for today, and I will see you on Tuesday.